Suppose now that d, m, and n are integers. If the number d divides m and d also divides n, then d would be a common divisor of both m and n. The largest or greatest common divisor of m and n is denoted GCD of m and n, the greatest common divisor of the two integers m and n. And a related definition says that if the greatest common divisor of the two numbers m and n is 1, then m and n are called relatively prime. Now, it does not mean that either of the two numbers is prime. It just means that they don't share any common factors other than 1. So as an example, the greatest common divisor of 8 and 15, well, what would that be? 1. So 8 and 15 are relatively prime. 8 would be 2 to the third power, and 15 would be 3 times 5. So they share no common factors, of course, other than 1. So they're relatively prime. Well, notice that, let's take the number 15. The divisors of 15 would be 1, 3, 5, and 15 itself. And the divisors of 25 would be 1, 5, and 25. I think that's it. So from here, we can ascertain that the greatest common divisor of 15 and 25 would be what? 5. The only common divisor that they have other than the number 1. Okay. Now, the last thing we're going to look at in this video is called the division algorithm. Now, it's called the division algorithm. It's not really even an algorithm. And this was found in Euclid's Book of Elements, in specifically book number 7. And what it says is, if you take any two integers, a and b, and make b a positive integer, or you could say that's a natural number, it's 1, 2, 3, dot, dot, dot. There's a unique pair of numbers, q and r, integers, such that a is equal to qb plus r, and the number r is in between 0 and b. It cannot equal b. It has to be less than b, but it could be 0. And if you haven't figured out, the q and the r really stand for a quotient and a remainder. So a is equal to qb plus r. So let's just do that with a couple, use this division algorithm with a few different pairs of numbers. So a, 14, is equal to 7 times 2 plus 0. So what would that be? That's a equals, 7 is our quotient, 2 was our b, plus the remainder r. In this case, there was no remainder. Why is that? Well, it's because 2 goes evenly into 14. All right, let's take a equal 1. 1 is equal to 0 fives plus the remainder 1, just like that. So a is 1 and b is 5. Our quotient, how many times does 5 go into 1? 0 times, with a remainder of 1. How about 23 and 7? So 23 is equal to, what's that, 3 times 7? That'd be 21 plus a remainder of 2. And in all these cases, remember that r is always less than b. 0 is less than 2, 1 is less than 5, 2 is less than 7. If 2 were not less than 7, if it were 8, that wouldn't be the correct remainder. We'd be able to increment this quotient by another one. So this is being very specific, this division algorithm. The last one is the one that might give you a little bit of trouble if you haven't seen this before. Well, what number do you multiply 7 by to get negative 59? Not exactly, but close to that. Well, 7 times negative 8 would be negative 56. But then what would the problem be? The problem would be that the remainder is a negative number. Negative 3, I think, right? So we have to put negative 9 times 7. So now we have negative 63 plus what would give us negative 59? Plus a 4. So our remainder, remember, our remainder's got to be positive, or at least non-negative. It's got to be between 0 and b. Can't be equal to b, it's got to be less than b, but it has to be at least 0. That's why we had to go to negative 9 instead of negative 8 in this case.